Hello everyone, my name is Sheikh Roshan Ramir. I am from Computer Science of Engineering Department from Institute of Aeronautical Engineering College. Now let us discuss about the introduction to Hamiltonian path. The definition of Hamiltonian path: a path that visits each vertex exactly once. If such a path exists in a given graph, the graph is said to have a Hamiltonian path. Hamiltonian paths are a fundamental concept in graph theory with applications in computer science, operation research, and more. They represent a path that visits each vertex in a graph exactly once, providing insight into the structure and connectivity of complex networks. The characteristics of Hamiltonian path. A, a Hamiltonian path does not necessarily visit all edges. If the path starts and ends at the same vertex, it forms a Hamiltonian cycle or Hamiltonian circuit. Example: the simple example of Hamiltonian path. Consider a triangle graph with vertices a, b, c. A Hamiltonian path here could be a to b, b to c, or any permutation of these vertices. Applications: the applications of Hamiltonian path are useful in various fields: computer science, biology, and etc. Definition of hypercubes: geometric representation, dynamic dimensions and vertices, graph representation. A hypercube is a geometric object that represents the n-dimensional generalization of a cube 2D and a cube 3D. It is constructed by taking the Cartesian product of n copies of the interval 0, 1, open brackets, closed brackets. Dimensions and vertices. In an n-dimensional hypercube, there are 2 power n vertices, each representing a unique combination of 0 and 1. The edges of the hypercube connect vertices that differ in exactly one coordinate. Graph representation. Hypercubes can also be represented as graphs where each vertex corresponds to a unique binary string and edges connect vertices that differ in exactly one bit position. Dynamic programming, used for specific problems like the traveling salesman problems. Backtracking, systematically explore paths. Backtracking when a vertex is revisited or a dead end is reached. Complexity of Hamiltonian paths in hypercubes. The problem of finding Hamiltonian paths in hypercubes, which are paths that visit every vertex in a hypercube exactly once, is known to be computationally complex. In fact, it is an NP-complete problem, meaning that there is no known efficient algorithm to solve it for large-scale instances. It what the 2 power n is a vertices and its dimension is n. The number of vertices in a hypercube grows exponentially with the number of dimensions, making the search for the Hamiltonian paths increasingly challenging as the cube size increases. Additionally, the number of possible paths also grows exponentially, further contributing to the complexity of the problem. Exciting algorithms for a Hamiltonian path. Brute force, a simple but inefficient approach that checks all possible paths to find a Hamiltonian path in a hypercube. Dynamic programming, the reservoir structure of hypercubes to efficiently compute Hamiltonian path using memoization techniques. Backtracking, a more algorithm that systematically explores all possible paths. Backtracking when a dead end is reached. Approximation, algorithm that provide good approximate solutions rather than the exact Hamiltonian path to address the problem's complexity. Brute force approach. First we have to generate it. Then second we have to check it. The last step is to select. First, list all possible Hamiltonian paths and then verify if each path is valid. Then last step, choose the shortest valid path. The brute force approach to finding a Hamiltonian path in Hypercube involves generating all possible paths and then checking each one to determine if it is valid. This exhaustive search method is computationally expensive with a time complexity of making making it impractical for large hypercubes. However, hypercubes it serves as a fundamental foundation for more efficient algorithms that leverage backtracking and dynamic programming techniques. Backtracking algorithm. Explore systematically. Backtracking algorithm work by systematically enumerating all possible solutions, checking if each solution satisfies the constraints of the problem, and then abandoning a candidate. Backtracking as soon as it determines that the candidate cannot possibly completed to a valid solution. Second one is build partial solutions. The algorithm builds candidates to the solutions incrementally, abandoning a candidate. Backtracking as soon as it determines that the candidate cannot possibly completed to a valid solution. The last third one is reservely, reservely traverse. Backtracking algorithms often use recursion to explore the solution space. They build partial solutions, test if they meet the constraints, and then either add to the solution or backtrack to explore other options. Dynamic programming techniques. First, tabulation. Second, memoization. Third, overlapping subprograms. First, building a table of solutions to subproblems, then storing and reusing solutions to avoid redundant calculations. The last one is to identifying and solving common subprograms efficiently. Dynamic programming is a powerful algorithmic technique for solving complex problems by breaking them down into smaller overlapping subprograms. By building a table of solutions to these subprograms and reusing them, dynamic programs algorithms can efficiently find optimal solutions to Hamiltonian path problems in hypercubes, even for large instances. Approximation algorithms, heuristic approaches, guaranteed bounds, greedy strategies, randomized algorithms. Heuristic approaches. Approximation algorithms use heuristics to find near optimal solutions to Hamiltonian path problems in hypercubes. These algorithms trade off optimality for computational efficiency, often providing good results in a fraction of time required for exact solutions. Guaranteed bounds. Many approximation algorithms for Hamiltonian path in hypercubes can provide guaranteed upper bounds on the distance of the solution from the optimal. Greedy strategies. Greedy algorithms that make locally optimal choices can be effective for finding Hamiltonian path in hypercubes while not guaranteed to be optimal. These approaches are often fast and can provide good solutions. Randomized approximation algorithms that explore the solution space probabilistically can also be used to find Hamiltonian path. These methods can be effective at avoiding local optima and providing high quality results. At last, the conclusion and future directions of Hamiltonian path and graph theory is Hamiltonian path is a fundamental concept in graph theory with significant implications in various practical and theoretical domains. Despite its computational complexity, understanding and identifying Hamiltonian path is essential for solving complex problems in network analysis, logistics, and optimization. In this final section, we reflect on the significance of Hamiltonian path in hypercubes and explore potential avenues for future research and applications. Thank you.